because of basically residual stress. It is now, you cannot say in terms of residual stress, but because of the these basically the defects which are getting accumulated in the grain boundary, so because of that it happens.
Okay, sir.
So okay, let me start. So last class we were talking about I know I have given you how to write the tangent constitutive matrix for a general case, and then we were discussing about the specific case. So if we are talking about the one Mises yield criterion, associated flow rule, and isotropic hardening, so for that we looked at the derivatives. So we are continuing with that. So let us say we continue with the just a minute. I think some problem. So let me close and open the file. Is the screen visible?
Yes, sir.
Okay. So let me continue with what we were doing in the last class. So we were last class where we were discussing the case corresponding to one Mises yield criterion, associative flow rule. So that means we have Q is equal to F and isotropic hardening. In case of isotropic hardening, alpha is 0. That is, alpha is a null vector. So this is the case we were talking about. So the moment we have this associative flow rule Q equal to F, and alpha is 0, that is isotropic hardening. So then Ct will be equal to elastic constitutive matrix C minus 1 upon A and del F by del sigma. So Q is equal to F, so we get this term into del F by del sigma transpose into C. So this is your Ct for the case of isotropic hardening, and where A will be alpha term will not be there in A. So A is del F by del sigma transpose into Ce into del F by del sigma. Q is equal to F, so we get this, and minus del F by del Wp into sigma stress vector into del F by del sigma. So this is the tangent constitutive matrix. So actually what we need in this, I have already last class I have discussed how to get del F by del sigma. So del F by del sigma, we have got that vector del F by del sigma xx and so on. So that is known, and in A also you have now this del F by del Wp. The other things are in terms of stress, so they are known. So we need to get this expression for del F by del Wp. So let us see how to get that. So we already know that for the one Mises yield criterion we have F, and for isotropic hardening this F is function of only stress and the plastic work of stresses, and we have seen that this is sigma xx square plus sigma yy square plus sigma zz square minus sigma xx into sigma yy minus sigma yy into sigma zz minus sigma zz into sigma xx plus 3 times tau xy square plus tau yz square plus tau zx square. So we have got this, and then minus we have this yield stress, and the yield stress is a function of plastic work, or you can say the equivalent plastic strain. So this is what is the yield function, and in this the first term actually whatever we have, this we also call it as equivalent stress. So you can also say that this is sigma equivalent minus sigma y, which is a function of plastic work of stresses. So this is your f, which is a function of sigma and wp. So now we want del f by del wp. So you see only this term is a function of wp. So when you write del f by del wp, so it will be minus del sigma y by del wp, because sigma y is the only term which is a function of wp, and usually we have this yield stress as a function of plastic strain. So we try to write it as minus del sigma y by del epsilon equivalent p, that is equivalent plastic strain, and then del epsilon equivalent plastic divided by del wp. So we can write it using chain rule of differentiation, derivative of y with respect to epsilon equivalent p, and then the derivative of epsilon equivalent p with respect to del wp. So we can write it like this. So I think it is straightforward, you can follow that. Now we want to express this d epsilon equivalent p by dwp. So we know the expression for dwp, the plastic work of stresses. In the last class I have shown that this is equal to sigma equivalent into d of epsilon equivalent p. This we have seen in the last derivation I did in the last class was this. So from this you can actually this differential relationship can also be written as d epsilon equivalent p by dwp is equal to 1 upon sigma equivalent. From this relationship you can write that, and because we are on the yield surface, elastoplastic loading of the material, so f is equal to 0. So f equal to 0 means sigma equivalent is equal to sigma y. So this is 1 upon sigma y. So then you can say that this basically del f by del wp will be equal to minus del now let me write the second term first. So we have this del epsilon equivalent p by del wp as 1 upon sigma y, so I can write that as 1 upon sigma y into d sigma y by d epsilon equivalent p. So we can write this term like this, del epsilon wp by. Now how do we get this d sigma y by d epsilon equivalent p? So now in the uniaxial case we know that epsilon equivalent p is equal to sigma xxp, and sigma y will be then the yield stress in uniaxial case, that is value of sigma xx. So
Sir,
it be
one doubt
yeah,
is,
yeah,
sir,
tell
we
me.
are able to replace sigma equivalent by sigma y because we are
Yeah,
assuming that currently, like yielding is happening, right, sir?
yeah, right,
That is why
yeah,
f equal
right,
to 0.
yeah, correct.
Okay, sir.
So we are on the yield surface, yielding elastoplastic loading of the material is happening. So we are on the yield surface f equal to 0, and that gives you sigma equivalent is equal to sigma y. So now we want to get this df sigma y by d epsilon equivalent p. So how do we get? So we get this data from the uniaxial loading. So if you consider the uniaxial loading, so let us say you have a sample and load it in UTM, and basically you apply the uniaxial state of stress, and then you get your stress strain curve from the uniaxial test. So you have here sigma xx, epsilon xx, and your stress strain curve is initial. So this is initial yield stress, that is sigma y naught, and then you have and we know that the slope of this is Young's modulus E, and when we unload it from any point, so now if we look at the slope of this actually, so this is in the elastoplastic region, this slope is referred to as ET, tangent modulus. And out of this, if you look at, if we unload it from any point, so we have already talked about that, so we unload it, so this is your epsilon xxp, and if we look at this, so this is your sigma xx e, elastic part of the strain. And if we just look at the from this point to this point, so this would be d of sigma xx, and now in this you will have total d of epsilon xx, and out of that, no, this is d of epsilon xx p, and this will be d of epsilon xx e. So we have already discussed this. Now how do we get the curve for yield stress versus plastic strain? So from this data, at any point, we know that at this point the stress is sigma y naught and the plastic strain is 0. And so similarly at any other point, this point we can draw a line parallel to initial elastic line and get what is the corresponding plastic strain, so that we can, for the entire curve, we can get at each point what is the stress and what is the corresponding plastic strain, and then from that data we can plot a graph between the now the stress sigma xx. This sigma xx is also no, for the multi-axial case, no, this sigma xx is actually say taken as sigma equivalent, and this axis we have epsilon xx p, and for the multi-axial case there would be epsilon equivalent p. So for that we get this kind of a curve. So here this stress is sigma y naught, and then other places you get this stress. Now if you take any 2 point and look at the slope of this curve, so that is known as plastic modulus h, and this stress is of course the incremental stress is d of sigma xx. So now you have basically here E is Young's modulus. You already know that E is Young's modulus. In the the stress versus total strain curve, the slope of the initial elastic part is Young's modulus, and then ET, this ET here. Now in the stress versus total strain graph in the elastoplastic region, when we go from one point to another point separated by a differential stress d sigma xx and differential total strain d epsilon xx, the slope of the curve is that ET, and ET is known as tangent modulus. And then we have this h. H is when we get the graph between the stress sigma xx and the plastic strain epsilon xxp. In that graph, when we take two different points separated by a differential stress d sigma xx, so the corresponding separation in the strain is d of epsilon xxp. So that slope is actually h, and it is known as plastic modulus. So in the graph I have explained to you. So now if you look at the
Hello, sir.
total strain, yeah, yes,
So can you please again explain that epsilon xxp graph you have drawn? How is it h you have taken?
yeah. So h is the slope of this graph. So you
So
take two
how?
points with a difference of stress as d sigma xx. So you take 2 points. So slope of this curve is your h. That is what I am saying. H is the slope of this curve.
Okay, sir.
Yeah, because d sigma xx is a differential change in
Sir,
stress, so h is
hello.
going to be the slope. Yeah, yes.
Sir, can we say tangent modulus is a function of Young's modulus and plastic modulus?
I'm going to derive that tangent modulus. I'm going to write a relationship between these three. So I'm just going to do that.
Okay.
So yeah, so if you look at d of epsilon xx from between 2 points which are separated by a differential stress or strain. So total strain increment d of epsilon xx is d of epsilon xx e elastic part plus d of epsilon xx p, and d of epsilon xx can be written as d sigma xx divided by et in this graph. So this d of epsilon xx total strain can be written as this d sigma xx divided by et, this et what we have. And similarly d of epsilon xx e can be written as d of sigma xx upon the elastic modulus e, and d of epsilon xx p can be written as the same stress increment d sigma xx upon h. So d sigma xx is common in all these, so you can say 1 upon et is equal to 1 upon e plus 1 upon h. So from this, if you want to get the plastic modulus, so h you can directly obtain. H is equal to, if you solve this equation, e into et upon e minus et, that is the expression you will get. So what you can do is, when you do the uniaxial testing, you get the stress strain graph, and in the stress strain graph from the elastic part you will get the Young's modulus, and then at different point you can draw the tangent and find out its slope, so you will get et, and once you have got e and et you can get the plastic modulus h directly. Of course, the other thing is that from this graph, the stress versus total strain graph, you can extract this stress versus plastic strain, and then whatever curve you get, the slope of that is h. And in general, h is going to be function of your epsilon xxp. And for multi-axial loading case, you will take the same thing as the function of epsilon equivalent p. So that is how you get these quantities, and therefore finally our interest is to get this del f by del wp. So we said that this is minus 1 upon sigma y into del epsilon equivalent upon del epsilon equivalent p, or we can say, you can say that this is uh, d epsilon equivalent is nothing but in axial loading case it is sigma xx. So you can say this is equal to, this is nothing but h, so minus h upon sigma y. So d epsilon f by del f by del wp is equal to minus h upon sigma y. So once you have this, then you can get your tangent constitutive matrix what I have listed here. So you can get, you can calculate a once you have all these quantities, and then you can calculate ct. And once you have ct, you can get your tangent stiffness matrix for the element. You can calculate the load vector, assemble all the elements, apply the boundary condition, and solve for the incremental displacement, and then continue this process. So usually in the softwares, if you see, there are most common models are, of course there can be a general nonlinear elastoplastic curve. The sigma equivalent versus epsilon p equivalent curve could be a general nonlinear curve, but sometimes this is simplified by what is known as either bilinear model or a multilinear model. So in bilinear model, what is done is, bilinear model, so in bilinear model, you have the only the whole stress strain curve is in terms of two straight lines. So you have sigma xx and you have epsilon xx, and the whole thing is, we assume that slope in the elastoplastic region is constant. So that is, this slope is e, and this slope is et, and this is sigma y naught. So what you need to know for this, you need to know EET. This is constant in this case because this is a straight line. Bilinear means two linear relations. So one straight line relationship is this, another straight line relationship is this. So you need E, you need sigma y naught, and you need ET, and based on that you can do your rest of the calculation. So this is known as bilinear model. So sometimes in the softwares you will have this bilinear. You can choose when you go to the elastoplastic model, you can choose the bilinear model if your stress strain, experimental stress strain response of the material can be accurately represented by this. Then there is a multilinear model. So in multilinear model, then what is done is you have this stress strain curve. So here you have say sigma xx. When we get we are approximating the actual stress strain curve which we get experimentally into multiple straight lines. So one initial is the elastic, and then you have this curve, this curve. Now you can have a little still a higher slope. So like that you can approximate into different straight lines. So this is here sigma y naught, and then you will have corresponding to this, let us say this is sigma y1, and then corresponding to this point this is sigma y2, and the slope of this is Young's modulus E, this is et1, this slope is et2, and the slope of this is et3, and so on. So you can also approximate the actual stress strain curve in this fashion, and then you can calculate, you can do your elastoplastic analysis for this. So this is what I wanted to discuss in the one Mises yield criterion, associative flow rule, and isotropic hardening. The next thing is kinematic hardening.
Sir, one doubt. Like the
Yeah,
stress strain curve here we are using, are these for true strain or for engineering strain, sir?
yeah, actually true strain, true stress, true strain curve. We are taking here true stress, true strain curve. Yeah, yeah, it's actually true. Thanks for pointing that out. So what we are taking here is the true stress versus true strain curves. So
And
now
sir,
the next, yeah,
sir, the derivation which we have done till now, so will it be valid for anisotropic material as well?
you will have different yield function for an isotropic material, but otherwise the steps involved and the derivations are similar for an isotropic also. The difference would be in the yield stress for an isotropic material. The
So
yield,
you
no,
can,
the yield function would be different for an isotropic material. So there are
okay.
different yield functions for an isotropic material. Otherwise,
For,
other things are same.
it will be direction dependent, right? We cannot specify like
Yeah,
uniaxial yield.
yeah, that's what you will have to get that's why that's what I'm saying, that you have to when you use the CE matrix, so one difference is going to be there in CE, and another difference is going to be in yield function. Yield function also would be different for the anisotropic material, and the CE matrix will also be different.
Okay, sir. So this all derivation which we have done is for isotropic, right?
Yeah. So far whatever we have done is isotropic, but if you use appropriate yield function and the constitutive matrix C, the expression for CT will be same. No, the tangent constitutive matrix is going to be, the expression is going to be same.
Okay, sir.
No, your F function, F yield function would be different. The C matrix would be different.
Okay,
Okay.
sir.
Yeah. So the
Sir,
next time, yeah, yes.
sir, like if associative flow rule is not used, then like CT can be non-symmetric, right?
So yeah, it can be non-symmetric. Yes.
But it will be symmetric in case of associative flow rule.
Yeah.
Okay.
So the next B, let us consider again one Mises yield function. Associative flow rule. Most of the metals you use actually associative flow rule. It's only like soil, concrete, and all the non-associative flow rules are used. So Q is equal to F, and kinematic hardening. Now we are considering only kinematic hardening. There is no isotropic hardening. The yield surface is not expanding, only translating. Kinematic hardening. So that is what is the next thing we are considering. So now, as I said, in kinematic hardening, yield surface translates. So if you remember the equation of a circle, So suppose now we want to relate the x and y. So we have, let us say this is y and this is x. The origin of the sorry, the center of the circle is, let us say, not at the origin but at some point. No, the center coordinates are, let us say, h and k, and radius of the circle is r. So in this case, the equation of the circle is x minus h whole square plus y minus k whole square is equal to r square. Or you write this as x minus h whole square plus y minus k whole square square root minus r is equal to 0. So you write this kind of an equation. So same thing we do for the yield function for kinematic hardening. In kinematic hardening, the basically yield surface is translating. So origin of the yield surface is now, the center of the yield surface is not at the origin but at some stress which we call as back stress. So in that case, your yield function f, which is a function of now sigma and alpha, back stress alpha. Sometimes in the literature alpha is denoted as actually x, and now the constant yield stress sigma y naught, that's a constant one, and this is equal to the whole thing is going to be no the under the square root sign. So let me write all the terms over here. So you have sigma xx. Now similar to this equation what we are writing over for the circle, so same thing is here, sigma xx minus alpha xx whole square plus sigma yy minus alpha yy whole square plus sigma zz minus alpha zz whole square, and then we have minus sigma xx minus alpha xx into sigma yy minus alpha yy minus we have sigma yy minus alpha yy into sigma zz minus alpha zz minus sigma zz minus alpha zz into uh, sigma xx minus alpha xx. So you will have the terms like this, and plus you will have 3 times tau xy minus alpha xy square plus tau yz minus alpha yz square plus tau xy yz and tau zx minus alpha zx whole square. So this whole thing is inside the square, the square root sign, and then finally we have minus sigma y naught. So that is your yield function in this case. So I hope it is clear, although I have written it, no, I should have written in a single straight line, but yeah, I think you can understand that all these terms up to tau zx minus alpha zx whole square, they are inside the square root sign, and then this minus sigma y naught is outside the square root sign. So that you should understand. So this is the definition of yield function for kinematic hardening case. And if we have mixed hardening, let us say kinematic hardening is also there, isotropic hardening is also there, so then this part which is there inside the square root sign will remain same. Only thing, this sigma y naught will become sigma y, which would be function of epsilon equivalent p. So that will become mixed hardening. That means kinematic hardening, and also there is a isotropic hardening. So that is what you will have if you have this. So now to calculate the tangent constitutive matrix, we need
Sir,
delay by this. Yes.
sir, why did you write WP?
Why did I write?
Why didn't you write WP in if
No,
is
I have,
function?
here I have written sigma of alpha and sigma y naught. No, in this one. You are talking about the isotropic hardening case?
Oh, okay.
Yeah, in this I have written only sigma alpha and sigma y naught. I haven't written WP because now we are considering only the kinematic hardening. For isotropic hardening, I had written
Yes,
sigma
yes.
WP. So now to further tangent constitutive matrix, you need del f by del sigma, you need del f by del alpha. So let us see, and also you need the Prager's constant, because when we talk of evolution of back stress alpha, we need the Prager's constant, the simplest model. So I will show you how to get del f by del sigma, how to get del f by del alpha, and how to get the Prager's constant C for this case. So now if you look at the del f by del sigma xx, so approach is similar to what we did for the isotropic hardening. So this whole expression, first you differentiate with respect to what is there inside the square root sign. So because it is whole to the power, power 1 by 2, so you get that power 1 by 2, and then in the denominator you get this whole square root quantity, because you will get whole to the power minus 1 by 2, so that can be written as this sigma xx minus alpha xx whole square, and plus all other terms. Now here you will get the entire set of terms, and then when you differentiate what is there inside the square root sign with respect to sigma xx, you will get twice of sigma xx minus alpha xx, that is from this term, that is what you will get. Then one term you are going to get from this, one term you are going to get from this one. So similar to what we did earlier, only thing is this alpha is the additional thing which is there. So you'll get minus sigma yy minus alpha yy and minus sigma zz minus alpha zz. So this is what you will get. So this is what you are going to get, and so we can write this as, I can say that del f by del sigma xx is equal to now see, because we are again on the yield surface, the material is yielding, so f is equal to 0. So whatever is there inside this square root sign, that would be equal to sigma y naught. So we can write this as twice of sigma y naught, and then what we have in the numerator, we can actually write sigma terms together and alpha terms together. So you can write that as twice of sigma xx minus sigma yy minus sigma zz, and then minus you can write twice of alpha xx minus alpha yy minus alpha zz. You can write it like this, right? And now we can write this in terms of deviatory components. So you can say that del f by del sigma xx would be equal to 3 upon 2 sigma y naught. Now this sigma y naught is constant, that is the initial yield stress of the material, and in the numerator what you will have is this sigma xxd minus alpha xxd. We have already defined earlier the sigma xxd, so that where this alpha xxd is twice of alpha xx minus alpha yy minus alpha zz divided by 3. So this is your alpha xxd. Now so similarly you can write you can say del f by del sigma yy would be 3 upon 2 sigma y naught into sigma yyd minus alpha yyd. Deviatory components of stress and deviatory component of back stress. And similarly we'll have del f by del sigma zz as 3 upon 2 sigma y naught into sigma zz minus alpha zz. So you can similarly define alpha y by d and alpha zz the way epsilon alpha xxd is defined. And then if you look at del f by del tau xy, so you will find that this will be again same 1 upon 2 into whatever we have inside the square root sign, sigma xx minus alpha xx whole square and other terms. And then this will be when you differentiate what is there inside the square root sign. So you are differentiating now this term. So 2 into 3, that will be 6 into tau xy minus alpha xy. So you will get here, this is 6 into tau xy minus alpha xy. So you can, as you see, you can write this as 3 upon sigma y naught into tau xy minus alpha xy. You can write like this. So similarly you can say that del f by del tau yz would be 3 upon sigma y naught into tau yz minus alpha yz, and del f by del tau zx would be equal to 3 upon sigma y naught into tau zx minus alpha zx. So these are the derivatives of stress. So now you have all the 6 components of del F by del sigma are written in terms of the stress components sigma and the back stress components alpha. So now you also need in the tangent constitutive matrix, you also need del F by del alpha. So let's look at its components. So now the components of del F. No, now let me look at del F by del alpha xx. So again, first 1 upon 2 into inside this is square root sign, whatever we have, sigma xx minus alpha xx whole square and so on, all those terms. And then in the numerator now, if you see, so what we will have is you will have another derivative of the first term. So you are going to have uh, twice of sigma xx minus alpha xx, but then the derivative with respect to alpha xx, so you will give you get you minus sign, so twice of sigma xx minus alpha xx into minus 1, that is what you will get. And in others also will get minus, so minus minus will become plus, so sigma yy minus alpha yy plus you will get sigma zz minus alpha z. So it's a straightforward differentiation. So if you do now you can do yourself and cross check that what I'm writing over here. So then you can write this as basically in terms of uh, uh, you can write it as let me write it as minus sign, let me take common throughout, so I can write minus 1 upon 2 sigma y naught, and then inside I can have twice of sigma xx minus sigma yy minus sigma zz and minus twice of alpha xx minus alpha yy minus alpha zz. You can check this, that is what you will get. And now we write this in terms of deviatory components. So we will have minus 3 upon 2 sigma y naught into sigma xxd minus alpha xxd. So that is what you have finally, del f by del alpha xx. So you will see that this is actually equal to minus del f by del sigma xx. So this is equal to minus del f by del sigma xx as the expression you see. That is what you will have. So now you can see similarly for other derivative terms. So similarly you can say del f by del alpha yy will be equal to minus del f by del sigma yy. We have already got del f by del sigma yy. Del f by del alpha zz would be equal to minus del f by del sigma zz, and del f by del alpha xy will be equal to minus del f by del tau xy. Del f by del alpha yz would be equal to minus del f by del tau yz, and del f by del alpha zx will be equal to minus del f by del tau zx. So yeah, these are the relationship you get. So in the vector form you can altogether say that del f by del alpha actually is equal to minus del f by del sigma. For this, that is what what is the relationship we are getting. So now if you look at the tangent constitutive matrix that is required in the analysis, elastoplastic analysis, so this tangent constitutive matrix CT would be equal to CE, that's the first term, and minus 1 upon A into CE, and then the first term is del q by del sigma, but q is equal to f for the associative flow rule, so we have del f by del sigma, and then of course del f by del sigma term is there, so del f by del sigma transpose into CE. So now we have already got del f by del sigma, so you know you can get the tangent constitutive matrix for this A, the scalar A is del f by del sigma transpose into CE into del f by del sigma. So because associative flow rule, so Q is equal to F. And the second term is minus del F by del alpha, and del F by del alpha is minus of del F by del sigma. So minus minus plus you can write in terms of that, into Prager's constant C into this L matrix into del F by del sigma. So this is your A. So first you calculate your A, and then you calculate your tangent constitutive matrix, and then these calculations have to be done for each element at each Gauss point, because now you see this is a function of sigma, and sigma is going to change from one Gauss point to another Gauss point. So these calculations have to be done at each Gauss point of the element. So these calculations are to be done at each Gauss point, and once you get CT, then you get the tangent stiffness matrix, and the right hand side and all you calculate, assemble, impose boundary condition, and solve the problem. So now one more thing is, how do we get this Prager's constant C? This is the Prager's constant. When we have already discussed the Prager's rule for this evolution of back stress alpha. So now how do we get this? So that is what I am going to discuss next. Calculation of Prager's constant C. So how do we get, where is this coming? So we have already seen that in the relations like this, epsilon xx is C times d of epsilon xxp, and so on, the other two components. Similarly, we have said that d of alpha xy is C by 2 into d of gamma xyp, and so on, the other terms. So that is where this is coming. Now consider again, we are going to get this all the material parameter data from the uniaxial test. So again, now I have already explained you that if you have carry out the uniaxial test of the specimen, so you have sigma xx and sigma xx, and you get the stress strain curve, true stress strain curve, and from that you can extract the relationship between sigma xx and epsilon xxp. So this curve would be something like this, where this is initially distress sigma y naught, and then you have this curve, and this is d of epsilon xx, and this is d of sigma xx, and this is slope is actually equal to h, not e. This is slope is h. So this data you get. So that is what we are going to get this information about C from the uniaxial loading case. So if you consider uniaxial loading case, so now you have sigma xx is not 0, and uniaxial case, so other stresses, yeah,
So there it should not be d of epsilon xxp.
it is d of sigma alpha xx is C times d of epsilon xxp only.
In graph, sir, the right side graph which you
No, this is, I have written, this is d of, it is p, d of epsilon xxp, right, that's right, correct. Thank you for this correction. Yes. So sigma and the other stresses are 0. So sigma yy equal to sigma zz equal to tau xy equal to tau yz equal to tau zx is equal to 0. So all the stresses are 0, and you will have, I think I have discussed it already, that if for the uniaxial case you will have some alpha xx at a particular strain level, and alpha yy would be minus half of alpha xx and alpha zz. See, although the stresses are 0, but the back stress components are not 0, because they are coming from the plastic strain, and plastic strain along y and z is non-zero. So that is why similarly alpha z would be minus of half of alpha xx, and of course alpha xy equal to alpha yz is equal to alpha zx. They will be 0 because the corresponding strain gamma xy, gamma yz and zx are 0. So the corresponding back stress will also be 0. And if you want to look at the proof, how do we get epsilon alpha yy as minus half of alpha xx? So if you look at the, by definition, d of alpha yy is C into d of epsilon yyp, and now this is because we know for the plastic deformation, the plastic deformation is volume conserving. So the Poisson's ratio is 0.5. So we get here this as minus c by 2 into d of epsilon xxp. And see this minus c into d of epsilon xxp is d of epsilon xx alpha xx. So I can write minus half into d of alpha xx. So d of alpha yy is this. So you can say that alpha yy would be minus half of alpha xx. So you know that similarly alpha zz is minus half of alpha xx. So now for this, if you for this uniaxial loading case alone, if you look at your yield function f, so the yield function is going to be sigma xx minus sigma xx minus alpha xx whole square, and then plus you have sigma yy minus alpha yy whole square. So sigma yy is 0, alpha yy is minus half of alpha xx, so you will get plus 1 upon 4 alpha xx square. Similarly, the third term is sigma zz minus alpha zz whole square, that will give you 1 by 4 into sigma alpha xx whole square, alpha xx whole square, and then we will have minus sigma xx minus alpha xx into sigma yy minus alpha yy, so that will give you alpha xx by 2. So yeah, so the other terms are going to be minus then sigma yy minus alpha yy, so that will be minus half of alpha xx into half of alpha xx, and minus the third term sigma xx minus alpha xx into alpha xx by 2. So this is what you can get. For the uniaxial loading case, you can write your yield function, and outside the square root sign we will have minus sigma y naught. So this is your f. If you simplify, actually this expression can be written as, if you simplify whatever there inside the square root sign, so you can write that as sigma xx square minus 3 times sigma xx into alpha xx, and plus 9 by 4 into alpha xx square minus sigma y naught. So this is how you can write the yield function, the simplified form of the yield function. And then now if you write the for the continued elastoplastic loading, the consistency condition for this uniaxial loading case with kinematic hardening. So for the continued elastoplastic loading, we will have f equal to 0. So that means the whatever is there inside square root, that would be equal to sigma y naught. So one is f equal to 0, and the other condition is df equal to 0. And df equal to 0 means we have seen for the uniaxial load, f is function of sigma xx and alpha xx. So we can write that as del f by del sigma xx into d sigma xx plus del f by del alpha xx into d alpha xx. This will be equal to 0. And now if you substitute, get the derivatives of f with respect to sigma xx for this uniaxial loading case. You have to keep in mind that we are talking about the uniaxial loading case. So you get over here 2 upon 2 sigma y naught. You can cross check this. So you'll get sigma xx minus 3 by 2 into alpha xx. That is one term we get into d of sigma xx. And the other term we get again 2 upon 2 sigma y naught sigma xx minus 3 by 2 into alpha xx, and then into minus 3 by 2 into d of alpha xx. So this is what you get, and this is equal to 0. And so now sigma xx minus 3 by 2 alpha xx is common, so we can divide the whole thing by that, and 2 upon 2 sigma y naught is also common, so we can divide by that. So we get d of sigma xx minus we get 3 by 2 into d of alpha xx, and alpha xx is c times d of epsilon xx p. and this is equal to 0. And d of sigma xx is, you can write h into d of epsilon xx p minus 3 by 2 into c into d of epsilon xx p equal to 0. Now again d of epsilon xx p is common, so from here you get this Prager's constant c is equal to 2 by 3 into h. So if you know h, you can get c, and once you know the c, you can calculate your alpha. So this is how you will calculate the Prager's constant for this case from the uniaxial data. From the uniaxial tensile test data of the material, you will get basically this the c, the Prager's constant c. Now although I think I have not yet actually uploaded the assignment 2, so that I'm going to upload. No, the assignment 3 priori I'm telling you that assignment 3 will be based on elastoplasticity. So let me know, you can start working on that. So assignment 3 is going to be problem on elastoplasticity. So let us say you have a plate fixed at one end. It's a square plate. Dimensions are 1 meter by 1 meter, and the loading is, one edge is subjected to this load which is 60 Newton per meter. So now you have to just discretize this using only one element. So this is say 1, this is node number 2, this is node number 3, this is node number 4, and this is x coordinate. The displacement in this direction is u, this is y, the displacement is v, and the thickness of this is say 2 mm. So thickness is 2 mm. So what you have to do is for this problem, model using, so you have to know whatever you learned, you are going to make use in this model using 4 noded isoparametric element and find u and v, the displacement along x and y direction, for nodes 2 and 3. Now for this you need to consider one Mises yield criterion, associative flow rule, and isotropic hardening. And for this, the material data, let me give you the stress strain curve. So you will model that as bilinear. So you have sigma xx this side and epsilon xx this side. So this is something like this. So Young's modulus is this is E, and let us say it is 200 gigapascals, and the initial yield stress is sigma y naught, which is 200 MPa, and the tangent modulus ET is 200 MPa. So this is the stress strain data. So this is the next assignment I will be giving on third assignment on elastoplasticity. So yeah, this is I think this is what I wanted to discuss today. Now I'm stopping here. If you have any doubts and questions, you can ask.
So the loading is uniaxial, right?
Yeah, loading is uniaxial. Yes. The uniaxial. No. For this problem, because the x and y dimensions are comparable, so this will be under plane state of stress. So the non-zero components of stresses are going to be sigma xx, sigma yy, and tau xy. Of course, sigma zz, tau xz, and tau yz would be 0, but sigma xx, sigma yy, and tau xy would be non-zero. So this is plane stress problem. Plane stress. This is no, the material data I have given. This is for the uniaxial loading case. Yeah. So now, if you have any doubts and questions, you can ask.
So here force also we have to like divide
Pardon?
the force which is given 60.
Yeah.
That also we have to apply in steps.
Yeah, you have to apply in steps. Yeah, you will not converge if you take the full load in one go.
Like what should be the step size and how we will know?
Maybe you can take 6 newtons. So whole
Okay.
thing you can do in 10 steps.
Okay.
Yeah.
And sir, we have to take only one element, right?
Yeah, only one element. Yes. Yeah. So any other question? Anybody?
Do we have like any criteria for knowing how many steps we have to take?
That is based on the convergence actually. So because it's an iterative process, so usually what we do is we start with some load step, and if the solution is converging within 4 5 say iterations, then we continue with that. If it is taking more than 5 6 iterations, then you reduce the load step. If it is taking lesser than that, say just 2 or 3 iterations, you can increase the load step. So it is actually done iteratively. But
Okay.
yeah,
Sir, one doubt, like
yeah,
if we are taking steps for this force,
yeah.
then will we need more number of elements while modeling
No,
for
no, you don't need. You can work with single. Although the solution may not be a converse solution, but the assignment I am giving you with a single element. If you're looking at the accuracy, yes, you need more number of elements. But no, to just practice this plasticity, I am giving you single element idealization. Although it will not give you accurate results, that is for sure. But yeah, we are just getting to how to do the elastoplastic analysis for a simple problem. That is why I am giving this. Yeah, but you need more elements for the accurate solution, that is right. But to avoid the complexities associated with that, I am making it a single element. So you will use 2 by 2 Gauss quadrature, so 4 Gauss points will be there. So all the calculations you have to do at all those 4 Gauss points.
okay. And sir, like
So we have to
for
make it
assignment
in
two,
a
what will
individual
be
level or a group.
Yeah, I think you can work in a group of 4 students. Yeah, that it will be yeah, let it be a group assignment.
sir for assignment two, what will be the due date? Uh,
Yeah, I'm going to upload, so I think I will give after minor.
yes.
No, the due date will be after minor.
Okay, sir. Okay.
Yeah.
Assignment 2 is individual or is that also in a group?
That is in yeah, it is in groups. That is also in groups. Group of 4 students.
Sir, how we should form the group? Sir, like the TA will be forming the group, or we have to do it our own?
Yeah, you can do among yourself. You can do yourself.
Okay, sir.
Yeah.
Sir, in minors, it will be open notes or closed notes.
Yeah, it would be open notes. Yeah, the exam would be open notes.
Okay.
Yeah.
Sir, can we get some numerical for practice? Because like all of the things you have taught is like theoretical, but suppose if it comes, some numerical comes, so that we have some practice.
See, the numericals are because these problems have to be done through a computer code. So actually, the full-fledged numerical is not possible. Intermediate steps you one can do.
Okay, sir.
But I know the full prop, because as you see here, so many matrices are involved, so the manual calculations would be almost difficult to do.
Yes, sir. Yes, sir. That was my concern also. Like suppose
Yeah.
if it
Hmm.
paper directly. Okay,
No,
sir.
then I will give maybe some intermediate steps or some derivations or some conceptual questions. So that is how I will set the minor.
Okay, sir.
So any other question, anybody?
Exam on Saturday 9 to 10.
No, not Saturday. It is on Sunday.
Sorry,
Exam is on
Sunday.
Sunday 19th, and we will start say at 9, so it would be 1.5 hours. So 9 to it would be 10:30, and another 20 minutes for uploading the your solutions in the grade scope. So basically 9 to 10:30, and then 20 minutes for uploading. So the total it would be over at 10. You can say 10:50. Okay.
Yes, sir.
Hello. Yeah. So are there any other questions, doubts? I think I will bit more. I will discuss about the minor tomorrow. So yeah, but in any case, if you have doubts and questions, you can ask.
So time is running out actually.
Yeah. Okay. Okay. Yeah. So if you have any questions and doubts, yes, you can ask. Hello. Anybody else? Any question? Any doubt? Okay. So then let me stop. Thank you all for your attention.
Thank you, sir.
Thank you, sir.